Hello everyone, this is Mohamed Gad-Elrab from Max Planck Institute for Informatics, Germany. In this presentation, I would like to introduce our work, ExCut, Explainable Embedding-based Clustering over Knowledge Graphs. This is a joint work with Daria, Stepanova, Kien, Tran, Heike, Adel from Bosch Center for AI, and Gerhard Weikum from Max Planck Institute. Recent years have witnessed increasing number of knowledge graphs. These knowledge graphs are usually huge with many entities and relations, yet they have a sparse typing system or even no typing at all, which make them hard to explore and search by humans or experts. Hence, they require some abstraction and summarization to be in a readable format. One of the key summarization methods is clustering, where the entities are grouped into subsets representing different types. Let's see this example KG of anonymous potential COVID-19 cases, which will be our running example. It shows entities from B1 till B6. They are persons with relation to other persons or working place or places they have visited. If a data scientist wants to explore such a graph, or more specifically to find an insightful division for the entities P1 till P6, his task will be hard given the complex structure of the knowledge graph. We can generate different possible division using different existing clustering algorithms, yet it is hard to decide which one is better. Some algorithms offer a numerical score that can help in comparison, yet it is not human-friendly. Therefore, the need for human-readable explanation arises. And this is what we are going to discuss in the remaining of this talk. In this work, we aim at explaining the clusters based on the knowledge graph itself. For that, we model the cluster explanation as Horn rule, with an auxiliary head relation belongs to, which represent that any entity substituting X belongs to cluster Cj, if the body holds by the facts in the knowledge graph. Let's see some example. For the knowledge graph we have shown before, and clusters 1 in red and cluster 2 in green, possible or potential examples will be that for cluster 1, these are the people who are potential COVID-19 case, or it is male, or these people who worked with someone who was infected with COVID-19. While for cluster 2, we can see, for example, R6, these are the people who visited some risk region. Now, the question is how to differentiate which explanation is better. For that, we simply define the perfect cluster explanation as the explanation that fully covers the target cluster and only the target cluster. In other words, it should have high coverage for the target cluster and should be exclusive to it. Since the world is not perfect and noisy, we need to measure how close we are to this target. Therefore, we introduce the measure of exclusive coverage, which in simple words, reward for covering the target cluster and punish for covering other clusters. We do that by computing the coverage of the explanation to the target cluster, which is the ratio of the entities following the explanation to all entities inside the cluster, and subtract the average coverage for other clusters. Looking into our example, we can see that rules 1 and 2 got higher coverage than rules 3, despite being not exclusive or expressive. On the other hand, using exclusive coverage or their values reduced compared to the last one. After we have illustrated what do we mean by explanation and how to evaluate an explanation, now let's put everything together and define the problem of computing explainable clusters as given a knowledge graph, a target entities, a number of clusters, and an explanation language defining how the explanation should look like, and an explanation evaluation function. Our target is to find a split C for the entities in T into K clusters with explanations R such that the explanation's quality with respect to the KG is maximized. Before jumping to our approach, let's see what are the state of the art. The related work can be divided into domains. First, entity clustering attempts For example, relational clustering or embedding-based clustering. Secondly, explanation mining, such as Daria, which assumes high-quality clusters that are hard to obtain in practice, and it learns explanation for these good clusters. Also, in this area, rule learning approaches such as AME can be seen as relevant. However, they are geared towards learning predictive rules rather than descriptive ones. Up to our knowledge, none of the existing approaches target the two problems jointly. Therefore, we introduce ExCut to bridge both worlds by utilizing embedding-based clustering and symbolic rule learning iteratively to mutually learn coherent clusters with human-readable explanations. In a nutshell, we start by performing embedding-based clustering, then we use rule learning to explain its results before we utilize the rules to give a feedback to the embedding, aiming at enhancing the clustering results in the subsequent iterations. Let's start with the embedding-based clustering. Given a knowledge graph and potentially external sources such as textual sources, we train entity embedding, which are the vector representation that can be used during the clustering of any subset of the entities. Then we can get a clustering for these entities, which is good because we didn't have to do any manual feature selection, and embedding capture complex patterns and compensate for the missing triples. However, the results are not human interpretable. Let's look at our example. We don't know why these entities come together in cluster 1 and why these came to cluster 2. Therefore, we apply rule learning to explain the clustering results. We use the results as input to the rule learning procedure. We start by materializing the clusters as relation belong to. Then we learn rule for this relation and rank these results based on the exclusive coverage explained before. As we can see in the example, it suggests two potential explanations for each cluster. And as we can see, these rules capture some explicit structure for the entities in the knowledge graph. So we would like to utilize this to enhance the clustering procedure. Therefore, we introduce the rule-based feedback. We use rule-based deduction engine to infer new entity clusters assignments based on the rules. Then we want to feed this signal back to the embedding model. In this work, we decided on a data manipulation approach rather than re-engineering or redesigning the model itself, which allow us to adopt any embedding model. For that, we compile a set of training triples to fine-tune the embedding model. Now the question is how to create such training set. At this stage, our target is to utilize the inferred entity clusters assignments and the explanations producing them in creating training set to adapt the embedding into more cluster-friendly embedding while keeping its characteristics and benefits. In other words, we want to reflect the structures captured through the learned rules, yet avoiding overfitting the embedding model to them. For that, we investigated 4 different strategies. First, using entity clusters assignments directly as training data. For that, we add new entity representing the clusters. Second one is same cluster, where instead of adding entities for the clusters, we only add same as relation between the entities from the same cluster. Here, B1 and B2 belongs to the same cluster. Rules as edges, similar to the first one, but instead of using a single relation belongs to, we use rules and or explanations predicted the assignment as the name or the label of the predicate. By this, we add more clues to the training data, such as redundancy. As we can see, R3 and R4 are redundant here, saying that B5 belongs to C2, or conflict, such as R3 is suggesting that B5 belongs to C2, and R1 suggests that it belongs to C1, and we leave the decision for the embedding model. The last one is similar to this, to the third one, but we model the rules as entities. Coming back to our pipeline, now we compile the training set using one of the feedback strategies. In addition, we add some context triples from the KG. These are the triples or facts surrounding the target entities in the original knowledge graph, which should regulate the update, preventing the overfitting to the rules. The final output will be clusters of entities, each with their explanations. As we can see in our example, this is the first cluster on the left. Those are the people who got infected due to having a co-worker who has COVID. And this, to the right, it is people who got infected because of visiting a risk area. Now, to evaluate the effectiveness of ExCut, we conducted several experiments using several configurations. More specifically, for embedding-based clustering, we tested with two paradigms of knowledge graph embeddings: translation-based embeddings represented by Trans-E, and linear map embeddings as in complex. As a proof of concept, we used k-means as our clustering algorithm. For explanations, we set the format to paths of length up to 2, optionally ending with either a variable or a constant. We also tested with the 4 rule-based feedback strategies that we have explained before. We compare our approach against state-of-the-art relation clustering, embedding-based clustering, and a basic configuration of our method where there is no feedback. We just apply k-means on Trans-E and then learn the rules. For evaluation, we use 2 types of measures. The first measures are clustering quality measures. We do that through using standard measures such as accuracy, adjacent trend score, and more. And we also use explanations quality. We measure the final average coverage and exclusive coverage as intrinsic measures. And as extrinsic, we used weighted relative accuracy, which expresses unusualness of the pattern or the explanation. We performed the experiments on some commonly used relational data sets, such as IMDb, WebKB, and UWCSE. To compare with existing approaches, our system showed better performance than the baselines. More details can be found in the paper about that. I would like to show some interesting results on the large-scale datasets. Here we tested on 4K entities from Yago distributed over 3 clusters: songs, movies, and books. The following figure shows the performance of different configuration of ExCut with Trans-E compared to the baselines in brown, except for relational clustering, which did not scale for such large dataset. On the left side of the figure, we can see the clustering quality, and on the right side, we can see the explanations quality. We can observe that configuration same cluster and rules as edges both achieved high clustering and explanation quality simultaneously, while deep entity clustering approach achieved high exclusive coverage. It did not achieve that in weighted relative accuracy or in any of the clustering quality measures. Let's see some examples from the dataset of Yago. On the left side, we show the result of using k-means on Trans-E, then explanation without any feedback. On the right side, we show after applying the iterative method of ExCut. On the right, we can see that cluster 1 combined both songs and books, while the other 2 clusters are all movies. All rules has low exclusive coverage and weighted relative accuracy. While on the left side, we can see that the 3 clusters were reconstructed as songs, books, and movies, and the explanation gave an easy-to-read summary with high-quality exclusive coverage and weighted relative accuracy. Finally, to summarize, in this talk, we introduced ExCut, an approach for generating entity clusters with human-readable explanation. ExCut interleaves embedding-based clustering and symbolic learning. The explanations then are used to enhance the quality of the cluster through fine-tuning the embedding. We showed better results than the state-of-the-art and baselines. We have several future directions. One of them is eliminating the required number of clusters and investigating the ability of the different knowledge graph embeddings to capture the knowledge graph structure information, and maybe also using more complex rules such as rules with negations. I would be happy to get your question during the conference or afterwards over this email. Thank you for listening.